started. Welcome back to the University of Kansas Physics and Astronomy Colloquium. Today we have Professor Kaoru Hagiwara, who's very distinguished, a 79 PhD from Tokyo Metropolitan University. He was a postdoc at the University of Wisconsin at Madison, at DACY, the German laboratory, postdoc at KEK, served a term in Durham, England, and from 1986 to 2015 he was a member of the prestigious Particle Data Group and the premier scientific institution in Japan, KEK. I also looked online to find out that he has more than 12,000 citations at an average of 66 per paper, which is astounding. But if you include the Particle Data Group citations, he has 68,000 citations at 287 per paper, which is even better. So today we'll find out about physics potential of T2HKK. Professor Hagiwara. Thank you.
Yes. Can you hear me? Yes. Is microphone on? Okay, good. So today I'm talking about T2HKK. It's neutrino oscillation from Tokai. Tokai is, it will appear in my latest slides. It's east coast of Japanese main island. There is a proton synchrotron laboratory called J-Park, and that's in Tokai Bay Village. And it was used as a starting point of the famous T2K neutrino oscillation experiments, which means Tokai to Kamioka. Okay, and this T2HKK is a kind of I believe that this is my own idea, which I will explain to you why I proposed this as a good idea. And apparently, there is some hope now that it will be realized. Okay, and this I will tell. And this work has been actually I got this idea 14 years ago. So I asked some of my students. Those three are my ex-students. This is my old-time collaborator. Professor Ko is from Korea Institute for Advanced Studies, and Xiaofeng Ge is my last postdoc at KEK, coming from China, Tsinghua University graduate. So I will, and all of them contributed to this work. I was told that I should introduce elementary particle physics to all of you, and this is my version. Okay, actually I made it myself. Okay, and the important thing is we have building blocks of our all our materials, which we called quarks, which makes nuclei. Yeah, this UUD, two up and one down, is inside of proton, which is one of our nuclei. And electron is surrounding nuclei to make a proton. No, to make atom, neutral atom, which is essentially make all of us. Okay, and in the world there is also a particle called the neutron. That has down, down, up inside, and together with proton and neutron makes all those materials that you already know. Okay, and the electrons are just matches. Matches the number of protons to make everything neutral, so that we don't collapse. Okay, and that's how we are made. But somehow particle physicists found that we have friends of up quark, which is called charm and top. Also friends of down quark, which has a strange and bottom. And we know that they are friends because they have the same charge, electric charge, 2/3 and -1 over 3. You may think that it's very strange, but it's actually those numbers are the secrets of physics which make our world. Okay? And I can tell you that we do not yet know why. Okay? Brilliant ideas exist, and my most favorite one is called grand unification. It appeared in 1974, but in any case, it is not proven yet, so it's still a conjecture. Okay? But in any case, those are very important hints that charged leptons have -1, and because of this quantization of electric charge, our atom is completely neutral, exactly neutral, and that is really important for our existence. If there is a small mismatch, it's impossible for us to survive. And this grand unification idea tells us that this is so because quarks and leptons are not completely independent. They are part of the bigger thing. And because of this, their charges are quantized. And that is a beautiful idea. So in any case, somehow, we have absolutely no idea. But somehow, this set of UD, E, neutrino appears 3 times, and we usually call it first generation, second generation, third generation. But we don't know why. Their properties look exactly the same, just a copy. Electron, muon, tau, just a copy. And all our ordinary life is finished in the first generation. We don't need second or third for our living because, as I already told you, all atoms are made of up and down and electron. What this neutrino is doing, actually, we do have a radioactive, radiative decays of nucleus, right? And for instance, if we set neutron free, neutron decays into proton by emitting electron and antineutrinos. And through this process, actually neutrino always exists. Okay? And it's part of our ordinary life. Now, particle physicists learned that those interactions, the very first thing we learned is how atoms can be combined. Okay, so it is between the plus charged proton and negatively charged electron. The interaction is called electromagnetic interactions. That was formulated by Maxwell in old days, but we now in particle physicists call that this carrier of this electromagnetic force as photon. We usually write gamma. Okay? And these interactions is electromagnetic interactions, which makes atoms and materials. Now, inside of proton, there are 3 quarks. Okay? These 3 quarks are bounded by photon-like object called gluons. And these gluons mediate strong interactions, so it is responsible for making proton, neutrons, and nucleus. Okay? And in addition, for this beta decay and those weak decays, there is weak bosons, W and Z, which mediate weak interactions. And in our ordinary life, it's just a beta decays. And finally, in 2012, the Higgs boson was discovered, which has Higgs interactions, which actually goes to the next slide. Now, I copied the 6 quarks, 6 leptons, and 4 type of force mediator and the Higgs boson. Okay? At this moment, we don't have friends of Higgs boson. Okay? But we believe that those force carriers are kind of similar thing. In particle physics, they are all called gauge bosons. Okay? And those are called quarks and leptons. Now, let's study their masses. Okay? We use giga electron volt as units of masses, energy is mass times velocity of photon squared, right? mc squared. Okay, and so in the units of c equal 1, we can measure the mass of particle in units of giga-electron volt. Okay, and it goes from 0 to 170 around here. Okay, top quark is the heaviest of all the particles. Okay, and we find that Higgs boson is 125, G boson is around 90, and W boson is around 80. B quark is around 5 GeV, tau is about 2 GeV, charm is around 1 GeV, and strange is 0.1, down is 0.001, and it goes like this. And the important thing is that in the linear scale, we have only almost all the particles are here. It's zero. This is very, very peculiar as compared to what we know about the masses of fundamental particles here. And you see those numbers in black are the weight of the each nuclei. Yeah, and they are roughly, actually very interesting thing is this hydrogen atom mass is about 1 giga-electron volt in this unit. So actually, if we put all those things here, all of them are aligned here up to around 200 or so. Okay? So actually, our elementary particle masses are very similar to the masses of our nuclei. Okay? But in case of nuclei, we know that it is kind of a integer type, right? Yeah, 1, 2, 4, 6 or something, right? On the other hand, there seems to be no such rule here. Yeah? And because there are so many zeros here, so we use logarithmic scale to measure the masses. And then that is in the right-hand side. And this is the pattern we have. So now all those particles which appears in the linear scale are here, one category. Then the other quarks and up to electrons, all of the, except for top quark, all the rest are kind of distributed in this region. Very strangely. There's nothing here. All those neutral leptons, which we call neutrinos, are here. Looks very peculiar. Okay? And this is actually the reason why neutrinos are interesting. This pattern, it's very difficult for us at this moment to understand what this pattern is telling us. But this pattern suggests that, neutrino may be interesting because it's so light. Maybe it gives us some hint of mass generation. Mass generation is responsible, is the job of the Higgs boson. But Higgs boson is just discovered. We know very little about Higgs boson yet. But it is responsible for those small masses also. Okay? And also the very heavy one also. And in a high energy physics seminar 2 weeks ago here, I talked about the heaviest top quark coupling to the Higgs boson, yeah, because that's very interesting to study, right? But of course, this is also interesting. So this is my talk today, okay? This is a very simple introduction to neutrino oscillation phenomena, which is not so easy. As I told you, one important thing we notice is that whenever electron interact with is produced, we produce new electron neutrino together. And we already know in a very old stage, it was 50s or so, yeah, when second neutrino was discovered, they found that nu mu and nu e are orthogonal. They don't change to each other. Yeah? And because of this, we named that this neutrino is associated with electron. This neutrino is associated with muon. This neutrino is associated with tau, and it is named. Okay? But in 1998, physicists in Japan discovered that these nu e, nu mu, nu tau are mixture of something. Okay? Because they are orthogonal, which we already know, it should be a unitary mixture of something. And this is the picture which we have. Nu e should be a mixture of nu 1, nu 2, nu 3, which have definite invariant mass. Okay? And nu mu should be another mixture of nu 3, and nu tau is another mixture of nu 3. And if these are unitary, this 3 by 3 matrix makes a unitary matrix, then we know that this and this and this are all orthogonal, right? Okay, so they don't mix. Okay, but by doing a very special type of experiment, we can reveal that they are mixture. That is neutrino oscillation. Okay, I first show that this is written at in the beginning. We produce muon neutrino. Let's say that proton hits the target, produce charged pi plus, and phi plus decays to mu plus and nu mu. Okay, and this mu mu is expressed this way from this ansatz. Okay, now in time, nu mu propagate. Say in our case, nu mu is produced in J-Park Tokai, and it travels 300 kilometers when it is detected in Kamioka. Okay, and then time is passed, and once it is time passed, it can become electron neutrino because this nu 1 piece has a definite mass, so it oscillates according to the Schrödinger equation. Yeah, this energy is E1. This nu 2 piece oscillates with E2. Nu 3 piece oscillates with E3. If they have different masses, the energy, oscillation frequency is only very, very tiny bit different. Okay? And you know that if you have two oscillations, yeah, with very little difference, what happens? Yeah? You can do it with any instruments, right? You just make one frequency sound, another frequency sound very near. Then it is the difference of the frequency makes a very, very long something like this, right? Yeah. And this is what experimentalists can observe. And I show you that this after time t, the amplitude to produce nu e can be expressed, can be given like this. And you just put nu e hat bracket, so bra to this formula, and you find this. But these are given here, so we just replace this by the unitary matrix elements. And this is what we find. And the probability of finding nu e from nu mu after time t is just the absolute value square of this amplitude. It's just quantum mechanics. And you just do these calculations and use the unitarity of this matrix. We find this kind of expressions. And if you just square this first piece, it becomes the 4 times this unitary matrix element product squared times sine square energy difference times time over 2. Okay? So we call this energy difference times t as phase of oscillation. Okay? All neutrino oscillation phenomena is given from energy difference times t. Okay? And this phase I usually call it 3-1 and 2-1. Of course, there is also 3-2, but 3-2 is just a 3-1 minus 2-1, so don't worry. Okay? So if you just study this E3 minus E1t, and because this is the action, so in order to study its units, we should divide by Planck constant over 2, yeah? this is in natural unit it's 1, but in order to make a unit, right, we need to reintroduce this. And this energy difference is, we assume that E3 is mass of M3, and E1 is mass of M1. So then its difference is like this. But that in the difference, this main piece disappears, and the second piece is inside of square root. It becomes this over twice of this, right? And if you just do this arithmetic, you get this formula. And in units of, let me see, in units of electron volt square for here, and L in unit of kilometer, and energy in unit of GeV, we find this phase factor is 2.5. It's a good number, like this. And if you just go back to here, you immediately notice that if this phase is pi over 2 is 1, so the oscillation is maximum. Okay? So we call this as oscillation maximum. Okay? So oscillation is biggest when delta 3.1 is pi, but we actually, it is kind of opposite. We already know that this mass square difference is 2.5 times 10 to the minus 3 electron volt square. So it's something like mass square difference is, mass is order of 0.1 electron volt or smaller. Okay? That's what I wrote in the first logarithmic scale. Okay? And sorry, I'm sorry. So it's not good. And this becomes pi when L over E. You can easily do this arithmetic by using this. 300 kilometer over 0.6 GeV, which is actually T2K. The distance from Tokai to Kamioka detector is 300 kilometer, and the beam is fine-tuned such that the peak is around 0.6 GeV. This is because we already knew that it should be around this region, so they designed that the beam orientation to make this happen. And another point is not only here, but if you set the distance around 1 keV, then the oscillation maximum is around 2 MeV. This is actually reactor anti-neutrino experiments where Diabe and Reno measured the smallest angle. Okay? And then in addition, we have another independent phase, which is called between M2, neutrino 2 and neutrino 1. This is very important for dictating solar neutrino oscillations. And it is, the important thing is it's about 1/30 of the, this big phase. Okay? So the oscillation due to 2-1 oscillation becomes maximum when L over E is about 30 times bigger than this. For instance, 50 kilometer over 3 MeV. This is actually the kind of typical scale for come-round experiments, and Juno is aimed at on this in China. Okay? So in any case, all those different experiments, you can just use this formula and roughly guess which this. Oh, very important thing I forgot to tell. If you are using reactor neutrinos, okay, or solar neutrinos, it's fusion or decay. It is essentially MeV. Okay, so a few to up to 6, 7 MeV is the range of the neutrinos. Okay, there. On the other hand, if we start from pions and then it is around 0.5 GeV above. Okay, and important thing is if you do very high energy neutrinos, they don't oscillate because if you make the energy large, this is L over E is small, even for the size of the Earth. So it hits you before anything happens. Okay? So this is the typical thing which you need to understand. Okay? Now let's go to the next page. This is just a summary of our present understanding in 3 neutrino models. And actually, 3 neutrino models is very interesting that we have 3 masses, 3 angles, 3 phases. But actually, in order for you to understand this, it's not so easy. I need to spend, maybe at least 10 minutes to explain, why there are 3 phases, especially because it's 3 phases appears when neutrinos masses are made from Majorana type. And I actually, as a prejudice, as a theorist, I prefer Majorana neutrino over the Dirac neutrino. And that's actually, I always think about this and try to see how much we can learn about those phases. Okay? And so among those, actually, the neutrino oscillation experiments can measure only mass square difference. There are only 2. 3 angles we can measure and 1 phase. We cannot measure phi1, phi2 from neutrino oscillation. They can be constrained by neutrino-less double beta decay, okay? But not by neutrino flavor oscillation experiments. And as I already told you, the exact mass of the neutrino cannot be measured. Only their mass square difference can be measured by neutrino oscillation phenomena. So from the point of view of neutrino oscillation experiments, if we measure all 6 parameters here, it's complete. Now, what we already know is that we know this m2 square minus m1 square, that it's positive, and it is about 8 times 10 to the minus 5 electron volt square. Whereas for this m3 square minus m1 square, we know it's only absolute value. So actually, we do not know if neutrino 3 is heavier than neutrino 1 or neutrino 3 is lighter than neutrino 1. So this is called mass hierarchy problem. And CP phase is completely unknown. And among theta 2, 3, 6, theta 1, theta 1, 3, we know theta 1, 3, 1, 2, 1, 3 rather well. But for 2, 3, because it is too near to pi over 4, we don't know whether it is smaller or larger than pi over 4. And this is, of course, it can be exactly on top of pi over 4, but in any case, it's an important question which we need to answer. So now, this is already a key point. My proposal 14 years ago is to look at it like this. JPAC is here. This is Tokai. Okay? And Kamioka is here. And actually, JPAC beam is so designed that beam center is going into the Earth, okay? Such that in Kamioka, we are 2.5 degrees off the central. Okay? The reason why they did it is this. Okay? This is the neutrino energy spectrum, flux. So 1 GeV is here, 0.6 GeV is around here. You go up, go up, go up, and you see that if the off-axis angle is 2.5 GeV, 2.5 degree, then the peak is around 600 MeV. Okay? So this is perfect for studying neutrino oscillation, nu mu to nu e transition at 300 kilometers away from us. That's Kamioka. Okay? So they designed this way. Okay? So I knew it. And then I thought that, oh, where is the beam center going? And then we found that it goes into the sea between Japan and Korea. And then I studied, oh, what if there is another detector in Korea? Then I found that it can be between 1 degree and maybe any degree beyond 1 degree. Okay? This is interesting because at 1 degree, the beam is much broader. So we have many, many flux compared to 2.5 GeV around between 1 and 2 GeV. The distance is clear. It's about 1,000 kilometers now. Okay? Up to Kamioka, it's 300. Okay? But Korea is 1,000 kilometers. So it's about factor of 3 longer distance. Now, we can easily study the probability of nu mu to nu e transitions at SK, of course, as predicted. The oscillation is maximum at 600 GeV, 600 MeV. And actually, at 1,000 kilometer, also at the 600 kV, there is an oscillation, okay? But it's very narrow, okay? This is called second oscillation. The first oscillation moved to here. So the point is, the first oscillation point is pi. Delta is pi, okay? Delta is pi is fixed when L over E is the same, okay? So 300 kilometer over 0.6 GeV is about 500. Okay, when this 500 is fixed, then the oscillation is maximum. So actually, if you go to further 3 times further away, then you should make the energy 3 times bigger. So that's what is happening here. Okay, so this is the first pi, and this is actually 3 pi. If you study the oscillation. It's fun. And I noticed this, and I proposed. And please read this. This is my paper. It's actually my talk. It's a proceedings, okay, in 2004. Okay? So it's a good record. And I already studied. In old days, there was a first experiment was done from KEK to Kamioka, which is called K to K. But now Tokai is here. Tokai to Kamioka is about 300 kilometers. And I studied the off-axis angle dependence of the spectrum. Okay? Because I noticed this, I asked our experimental colleague to make this. So this is the very first systematic off-axis neutrino flux data we obtained from the experiment. Okay? It's coming from, actually, it is slightly site-specific. So this is a Tokai beam. And we found that about 1 GeV or 0.5 GeV, we have lots of flux around 1 to 2 GeV. This can be used. And this is a famous photo, but it's again 2004, 14 years ago. We already had it. And the beam center appears here. And around here, so this is 0 degree, 1 degree is here. So the tip of Korea can be as near as 1 degree to the beam center. So it is very hard. Okay? So this may be a very good place, I thought. Okay? And of course, the beam goes into deep if you go further. So we study the matter distributions along the beam baseline. Neutrino goes straight, but geology, we have a flat land, and we just dig into the how do you call it, vertical direction. So for geologists, this is a better way. So we just make it. Okay. And we study the consequences of this 1 beam 2 detector experiments. And one thing, I just skip this. The most important thing we noticed is that, in my example, I showed you the squared of the leading piece only. That is actually 4 times sine squared theta atom. So this is just a naming for a combination of unitary matrix elements I gave you. And sine squared theta, this is what I, sorry. So sorry, this product is the combination which I showed you. And then sine squared, so this phase over 2 is, you already remember, it was given in my simple formula. Okay? And because there are remnants, so I systematically obtain the next leading contributions and try to combine. And we found this formula, which is turned, even now it is useful as a guide. So of course, when delta 1,3 is pi, pi over 2 is sine square pi over 2 is 1, so it is very big. But first of all, we have this factor common, but we have additional contribution coming from subleading contributions. And I wrote it as a correction factor with 1 plus a. Okay? So this tells compared to the simple leading term, we have some additional contribution which makes the magnitude of this oscillation changes. And this A can be expressed this way. And this is the distance which for 1,000 kilometer. And if delta 13 is pi, then the correction can be as large as 0.37. So it is compared to 1. So it means that, first of all, if I told you that we do not know the ordering of the mass squared difference between M3 square and M1 square. Okay? It means that when delta pi 13 is pi, or pi or minus pi, sine square doesn't change, but this factor changes by plus minus 1. Okay? So depending on the hierarchy, actually, in one case we have 37% bigger if this is positive. If it is negative, it is 37% smaller. I thought that it's a huge difference. Okay? This should be measured. And then in addition, we found that by collecting other terms, that we found that this del sign of CP phase can be measured with this kind of factor with a definite sign. Okay? And this means that if this is 1, okay, then it can be 30% and smaller. If this is minus 1, okay, then this can be 30% bigger. Okay? So it means that if the hierarchy, this delta 13 is positive, we have 37% positive here. And if sine delta is negative minus 1, then it is also 30% bigger. So addition of this becomes almost 60% bigger than 1. Okay? This is actually kind of hint which T2K is already observing. Okay? And this can be seen very, very clearly from this. Okay? And important thing we found is that if we measure the same oscillation maximum at pi between 1,000 kilometer and 300 kilometer, then actually we find that if the oscillation is bigger at further distance, then this delta 13 should be big, positive. So we have M3 is bigger than M1. On the other hand, if it is opposite, like this. So hierarchy can be resolved simply by comparing the oscillation probability measured in two different places for the oscillation maximum. Another thing we found is this. Yes. Actually, this comes from matter effect. I skipped explanation of the matter effect. I'm sorry. Yes. And now it is a phase. Okay. So the location of the maximum can be shifted by this B factor. And you do this, and you find that this B factor is independent of mass hierarchy. It's just minus 30% corrections, plus cosine delta here. It's not very large, but 15%. So, compared to sine delta, it was 29%. So it is smaller, but with half accuracy, we can also measure cosine delta, right? Now, if you measure both cosine delta and sine delta, we can determine delta uniquely in principle. That was my idea. And this is just a recent story. 2 years ago, I received an email from Subon Kim, who is a leader of Korean neutrino experiments. He was a leader of Reno experiment. And they are now collaborating with the Hyper-Kamiokande team in Japan. And they are discussing the possibility of having Hyper-Kamiokande in Korea. Okay? Second Hyper-Kamiokande in Korea. And this is, they now call it T2HKK. I called my idea as T2KK because T2K is Tokai to Kamioka, and if I just add Korea, so T2KK was my naming, but now they have changed to T2H. but that's better because it's bigger, okay? And those are the sites. This is given to me from Subon Kim, and they already studied all my past papers, so they already knew that what kind of place is good, and so they look for the possible candidate sites in depending on off-axis angle, because we know that neutrino flux depending on the off-axis angle, okay? And I think I will just choose only one of them, okay? H. Site H is what I studied most carefully. It is called Mount Bissell, and it is actually this place has 1.3 degree of axis angle, so it is relatively hard. So we have sensitivity to large, first oscillation peak with this location, and it turned out to be giving a very good sensitivity. So this is the picture. As you already know, in 2004, 14 years ago, my collaborator, actually Naotoshi Okamura, could do all those, how do you call it? It's just a geometry, right? of what should be happening on the Earth, right? So it's very easy. So I just asked Naotoshi Okamura again that now they have candidate sites. Why don't we repeat it again? Huh? And this is what he found. So the beam center goes here, and Oki Island is the best candidate within Japan. But now, so this is Mount Bissell, okay? So the baseline goes like this. Oh, one important thing you notice is, the neutrino beam goes along this black line, okay? And SK is in the north side, and HK is in the south side. This is very interesting. They actually arranged this way intentionally so that in the future, if HK is approved, then from the same beam, they have exactly the same off-axis angle for SK and HK. And actually, because of this, the distance from SK and HK is about 8 kilometers, north and south. And this, again, can be used for another proposal, but I don't, yes?
Why not detune HK and SK, put them off axis so that you optimize total flux far away?
I beg your pardon.
You have a couple of options. So when you're putting one of the detectors off axis to take advantage of the energy distribution, but why make it the far detector? Because the far detector is harder to hit. You get less flux, 1 over r squared. So you don't have to. There's a lot of options. Has it been optimized in some engineering sense that you could put
if
the far one
you
on axis and the near one's off axis?
All those questions
the near one's quite a bit off axis.
All those questions I studied in 2006 to 8, around there, and actually, if you read my very old papers, you find that completely free float, and I just studied, yes. But it turned out that this type of place is the best, yes. And the neutrino flux, this is a T2K flux, and this is the one of the site which is very similar to T2K flux, and this is our best candidate. And at 1.3 degree, neutrino flux and anti-neutrino flux has quite significant contribution, about 1 GeV, which turned out to be very, very useful. And for the matter distributions, this is very easy to make, but the difficult thing is how the matter distribution is along here. Okay, this is our old work, but again, my collaborator used this kind of map. Oh, you need to understand that we are floating on the sea of mantle. Okay, so if you have lots of things like a mountain or island, okay, then the bottom of this crust is deep. Okay, if in the sea there is nothing, right? So actually, it's very thin. So it means that from our side, mantle is very near to us. Okay, yeah. In the center of the mountain, mantle is deep. It's very simple. Okay. So by using this, we can calculate actually those matter distribution along the baseline, and this is what we found for site H, which is our favorite one. Okay. And last week,
Where are the error bars on that?
there's no error bar. What I did is, no, it's okay. Actually, I know, of course, in old days, I studied all those geology papers, and I know that it is essentially the sound velocity they are measuring, and the error for the sound velocity is about 3%. Okay? But the important thing is, for this experiment, the overall correlated uncertainty is most important, not the individual velocity error. And because of this, I completely forgot it. There is a correlation between the velocity and the density. Okay, and then I found that this correlation curve had almost 6% kind of spread. So actually, I assigned an overall 6% uncertainty to all the normalization of the distributions. And actually, it turned out that is accurate enough for this type of experiments. And last week, September 12th, this year, we got great news from the chairman, president of University of Tokyo, that seed funding towards the construction of the next generation water Cherenkov detector Hyper-Kamiokande has been allocated by the Ministry of Education. Okay? The University of Tokyo pledges to ensure construction of the Hyper-Kamiokande detector commences as scheduled in April 2020. Okay? This is the kind of approval from the university, and if it really goes well, they start making Hyper-Kamiokande in Kamioka site 2020 April. It means that in about 5 years, 2025 or 26, the experiment can start. Okay. Important thing is Korean colleagues have been waiting for this to happen, and once this happens, they will ask their own government to support their second Hyper-Kamiokande. Okay, and my studies will be used toward their funding request. So actually, that's rather important. And we did some preliminary studies on this, and something like mass hierarchy, delta CP. So this is the 3 remaining things, because this is definitely you need to do. New physics search and those things, it can be done later. Okay? The standard model physics you should do first, and the project should have enough weight in this regard, right? Standard model physics should be extremely important. So all 3 remaining things should be resolved. That is our target. And this table is made as a communication between theorists and experimentalists. Actually, I have often collaborated with experimentalists, but I never worked together with experiments because I prefer to be completely free from experiments. And I always tell experimental colleagues that we should better be enemy rather than collaborator, because, we should be enemy, right? And that is the correct way of making progress in physics in the right direction. Okay? So, but still, whenever we make some simulations or results, we make every assumption crystal clear so that experimentalists can always reproduce our result instantly. Okay? This is very important, and also this is the window of discussions between experimentalists and theorists. And we give all the uncertainties we give, and sometimes they say that, oh, this uncertainty is too small, or this is probably too or overly pessimistic or something. And then we changed. Okay? And so this type of talk is rather important. Now, first we show the mass ordering results. It's quite astonishing. Now, this is, I already told you that first Hyper-Kamiokande is going to be approved, okay, start. And that is assumed to be there. And we are talking about the second Hyper-Kamiokande. And I compare the physics merit between placing the second one in Kamioka site and in Korean site. And this is the comparison. And in case of hierarchy, it is the definition. The conclusion is very clear. I knew that this conclusion, 14 years ago, that if no matter how much huge detector you put in Kamioka, if the baseline length is the same, there is absolutely no sensitivity to mass hierarchy, and this just proves it. So this is the double Hyper-Kamiokande in Kamioka, and of course, if we are lucky, we can exclude the wrong hierarchy with 3 sigma, but most of the case it's around 2 sigma. After 10 years, even if you do 10 years, well, you may be extremely lucky around here. Perhaps you can, but in most of the case, it's still 2 sigma, 3 sigma. Okay? Now, compare with the case with exactly the same total volume, one Hyper-Kamiokande in Korea. Okay? Within 1 year, this is what they obtain. No matter what the CP angle is, no matter what this octant unknown thing is, certainly 3 sigma is already can be done in 1 year. Okay? So it can be rejected. If it is a normal hierarchy, it is rejected like a solid line. If it is an inverted hierarchy, it is rejected in this fashion. Okay? Now, after 10 years, this is the results. So 5 sigma is here. So chi-square of 100, well. So it simply means that within 2 or 3 years, yeah, with the second Hyper-Kamiokande in Korea, they can declare 5 sigma determination of the mass hierarchy. This is very good. Now, the next one is CP phase. For CP phase, you tend to think that putting all the detector in near side is better because you have more events, right? Actually, I also thought so. And this is the CP measurement. We just studied 4 places, 0 degree, minus 90, plus 90, 180. And this is the chi-square curve. So it's essentially, if you read 1 sigma region, we roughly say that, this angle phase can be measured with 30 degree, plus minus 30 degree, plus minus 30 degree. But this is about plus minus 15 degree. So depending on the delta location, the error changes. Yeah. And after 10 years, it looks very, very good. Yeah. So this is about plus minus 5 degree. This is about plus minus 15, plus minus 15. Yeah. So this is what we can get with putting everything in Kamioka. Now compare this with one in Korea example. And actually, we find that these errors are very similar, plus minus 30 here, plus minus 15 here. Okay? After 10 years, actually, I didn't completely understand the reason. Okay? But this is plus minus 5, so this is very similar. But here, it is significantly better than everything in Kamioka option. So it's maybe plus minus 10 degree around here. Okay, So actually, placing a detector far away improved the CP phase measurement. And actually, part of the reason is very clear. This contains a second peak also. And second peak is 3 times more sensitive. You need to go back to my slides, so please let me refrain from doing it because I have only 5 more minutes. Okay, so but that is one of the reasons. But I really need to understand this more carefully because yes.
So this result include all the matter effects and the systematic uncertainties of the 6% you mentioned earlier?
Yes, of course, yes. And this solid line is for when the hierarchy is normal. Dashed line is when the hierarchy is inverted. So we don't give any any prejudice. Yes. And finally, the octant sensitivity, which is actually I noticed that I should have done even better. So from my previous experiences, I thought that it is extremely difficult to distinguish 0.45 and 0.55. So I studied 0.4 and 0.6. Now, with everything in Kamioka option, if the correct answer is 0.4, 0.6 is rejected at the 4 sigma. If the correct place is 0.6, 0.4 is rejected at 4 sigma. This is as I expected. And after 5 years, of course, it goes up. Okay? But now this figure suggests that probably we can also go near to 0.45 and 0.55. And this we will do in the next version, okay, of this study. Now, what would happen for Korean T2HKK? And it's very slightly worse than everything in Kamioka case, but still it's near the 4 sigma range. And after 10 years, again, it's very, very similar. Okay. So I think we find no rules within the standard model studies that placing in Kamioka, placing a second Hyper-Kamiokande in Korea has compared to everything in Japan. Okay. Okay, this in addition to the budget program, you know, if Korean government can contribute, that's much better. Okay, but from physics point of view, putting the second detector in Korea has perfect sense because hierarchy, mass hierarchy, can be determined within a few years, 5 sigma. Okay, and in addition, CP measurement is probably better, and for this I need to study a little bit better. Okay, but this is what we already find. Now this is my summary. T2HKK with site H can resolve the neutrino mass hierarchy at 3 sigma or 8 sigma after 1 year, 10 years. And the sensitivity of the CP phase delta is found to be very similar. So here I just said that it's similar. I didn't discuss the even better CP at Korea because I don't completely understand the reason. Okay? And octant generation can be also resolved. And actually, we compare 0.4 and 0.6, but probably we can resolve 0.45 and 0.55. That's very good, right? It's already almost perfect. And in my memory, this is the last. Oh, I made one more slide. We have not studied the correlation among systematic. So those are difficult problems, and maybe this can be done only with collaboration or with information from the experimentalists. And actually, once these experiments start, we should immediately, or even before, once it's approved, we should immediately start studying the possibility that if this setup can lead us to non-standard physics. Okay? That is very important. And non-standard physics are usually parameterized in terms of the non-unitarity of the 3×3 matrix. Okay? That is very important. It tells about stellar neutrinos, right? if stellar neutrinos mix with our 3 neutrinos, the unitarity within 3 by 3 is broken. So we should look for the non-unitarity. That is what we can do, okay? In addition to adding some short baseline experiments, okay? So we should explore all possible neutrino experiments, but we should tell what our 1 beam 2 detector experiments can add to this. And actually, we found this. As I told you already, that if we have 2, detectors with the same L over E along the same beam line, then we can determine both mass hierarchy and delta at the same time by comparing the two oscillation magnitude and phase in 2 locations. Okay? It means that I think we can split our whole analysis into muon neutrino only with half of the beam, okay? And anti-neutrino beam only data, and each experiment will determine the phase and the hierarchy. Okay? In this way, we can compare the results we obtained by neutrino beam oscillations and anti-neutrino oscillation beams, and if they agree, actually it tells that certain type of non-standard model physics is not coming, right? So it is very, very important that the experiment has, how do you call it, multiple handles. It is not sufficient to constrain all the parameters, all the unknowns, just in one way, but the same physical quantities should be measured in multiple ways. That is very important. Once you have multiple measurement, our conclusion can be very robust against other assumptions, or if we are lucky, we can find something different from the standard model by comparing the 2 types of constraints which should agree with within the standard model but can disagree with the presence of something new. Okay? So this type of study I have not done, okay? But this is a very general remark which you should always keep in your mind. This is all. Thank you very much.
So the currently there's planning for this June experiment, from last South Dakota. I think there's quite a lot of the same physics goals as this. Would you propose that they have a second experiment? Unfortunately, somewhere Kansas is probably too far south. Would you propose that?
Kansas. Splitting of the beam to the this and that. That's really very hard.
No, I'm just saying. It'd be good to. I understood that June was supposed to be able to do this mass hierarchy.
Yes, I agree. It's very easy.
So but I guess time scales are not going to be that different.
I think you should start very quickly.
So June also plans to start 2025, 2026. Their plan.
But we never know they would be successful in constructing Hyper-Kamiokande in 5 years. So maybe June is still ahead. Yes?
So if everything goes okay, then 2020 they start construction.
Yes.
And then 2025, 2026 they will start measuring the data.
Yes.
So what's the timeline? Is it for the data measurement, data taking?
Most likely, this T2HK will start first, and then maybe 1 or 2 years later, Hyper-Kamiokande in Korea can start.
No, I mean I'm talking of the one in Japan only. I mean Korea side is very uncertain. So.
as I told you, if it is in Japan only, T2HK has absolutely no power for mass hierarchy. Okay? The mass hierarchy information can only come from outside, like you. So it may also be nice in that sense that Dune and T2HK collaborate, and we can establish the mass hierarchy.
So then, what would happen to Super-K? Is there
Super-K will be there.
So to continue to
Yes.
take the data then, independent of
Super-K is now, evacuating all the water, and they are now preparing for gadolinium doped new Super-K,
I see.
which is aiming at diffused supernova neutrino detection.
More questions? Let's thank Kaoru again.